Looking good. Excellent. You got it right? Excellent.
Hello, folks.
Hey, John.
Hello. Trying to figure out how to get my slides up here. There.
Hopefully your audio works more reliably this time.
Yeah, I'm trying to figure out how to share. I'm not seeing my slides up here and share yet. So I'm a bit dismayed. Okay, well, I don't know if I can do it this way. I'm just going to try and share my slides. Can folks see my screen? I seem to have lost you there.
Yes, we can see you, but please use presentation mode.
Yes, I'm going to do that. Well, if you can't hear me, we are in a bit of trouble, but not for too long, because I won't be talking for too long. By saying welcome, this is the ICCRG meeting at IETF 14. If you meant to be somewhere else, this is more fun, I promise you, so just stay here anyway. I'm going to just very quickly go through and show you the note well. If you are not familiar with this, you should become familiar with it. And if you don't, if you're not familiar with this, again, hit me up. I'm happy to share this and talk to you about it. Know that the IRTF note well is a little bit different than the IETF note well. However, high level, it still applies. I'm not going to go over the goals of the IRTF. They are in the slides. You can look at this. The only thing I'll point out is that this is a room where we are not doing standards development. So remember that as we have conversation and discussion today. Finally, the agenda. We've got 3 topics today. Got Prague congestion control. Bob Briscoe and Vidhi Goel will be talking about that. I have, after that, the agenda slightly changed. We're going to have Natalia present packet reordering in multipath transport scenarios after that, and Colin will go talking about congestion control work, especially with respect to the new proposal in transport area about congestion control work in the IRTF and in ICCRG. So we'll spend the last 10 minutes or so talking about that today. That's all I've got. I want to quickly get somebody to do scribing.
I might as well do JavaScript again. Is anyone taking notes?
So much. Yeah, who's taking notes? We need somebody to take minutes. It's not going to be a lot. You don't have to take minutes through the presentations, just the Q&A for the most part. Hello, hello. Do you want me to assign a person? I can't see people in the room here and call out people. Who's in the room there?
It seems like Neil Caldwell is volunteering.
Oh,
Yes.
excellent. Thank you, Neil. All right. I will send you your gifts later, and I'll charge the IETF for it. We're going to go on to the first talk. Bob, you're already up there. Take it away. We got 30 minutes for this. Thanks, Bob.
I assume you're driving the presentation, are you? Jenna?
Sorry, you should be able to. You want me? I can do that if you want me to.
Well,
I'm
at a mic without any way of controlling anything. So.
Got it. I can do it. Hang on. Let me get it going.
Is that light up there? Right. Okay. So I had a look back and realized that when we've presented things about Prague congestion control twice in ICCRG before, we always just said the latest thing we'd done, and we never actually gave the sort of basic results. So this is what this is all about. There's the people involved in the authorship of the draft and the experiments that I'm going to go through. Next slide, please, Jenna. Yeah, so just some caveats. What you're going to see is comparative results between different congestion controls and different AQMs, and the primary reason is to share insights that we got from those, and you'll obviously get the numbers in the results as well, but the test traffic isn't designed to be realistic. It's designed to be explain these effects I want to talk about. So next. Right, so you've probably seen the right-hand picture first. The left hand of this slide is more what the congestion control, what the differences between DC-TCP and the congestion control are, and the right-hand side is the principles by which DC-TCP and Prague work. I'll start with the left, and I'm not going to go through all these. I'm just going to say, really, the list isn't that long, and that's why it's there. And this is what is in the draft to explain, assuming you start from DC-TCP, what the differences are. So on the right, I always explain the point of DC-TCP and scalable congestion controls generally as having small sawteeth, so you don't have a large variation in the buffer to get full utilization, and if you push down delay by setting the set point of an AQM low, you don't start losing utilization. So you get the best of both worlds. So next slide is going to be empirical results that prove that, just with a single flow. On the left is a cubic flow, ECN cubic in fact, to show that it's not ECN that's doing it, but it's the cubic-y part of it. Happens to be using FQ-CODL, but any classic AQM would do. And the left-hand column of results uses a 5 millisecond target, and the middle column uses a 1 millisecond target. And then the right-hand column is Prague over dual pi squared, also using a 1 millisecond target. The horizontal axis is a range of 5 link rates and 5 round trip times. So you've got 25 different cases for each column. And you've got Q delay and utilization as shown in the previous plot, now shown here. And you can see as you push down the Q delay set point for FQ-CODL from 5 to 1 millisecond, you do get lower mean delay, which is the blocks, and you do get lower 99th percentile delay, which is the little dots on top, but you lose out on utilization. The mean, which is the little bar in the middle of the horizontal bar in the middle of the vertical bar goes down to about 87, 88%, and you can see the first percentile and 99th percentile also, well, the first percentile goes down below 85% in the highest BDP case tested. Whereas on the right, you can see if you use a 1 millisecond threshold with TCP Prague, because of the small saw teeth, you get near 100% utilization as well. And that's just showing you proof of that point. Next slide. So this now, the next point I want to make runs over about 4 slides. First of all, when you look at a plot of delay, the little blue dots in the middle column, the columns are the same, by the way, the same 5 link rates, same 5 round trip times, giving you 25 of each case. But both plots this time are Q delay. And the trouble is, as with all delay metrics, smaller is better, so you can't actually see the good ones. Whereas if you show a log plot, which is what the bottom one is, you can see it's significantly below the other ones. And the other interesting pattern there is it's getting lower as the link rate goes up. Now, when you work out how many packets there are in the queue, you find that that's because as the link rate gets higher, by the way, as the round trip time changes, it doesn't change. So each step is flat, but the link rate is obviously making a difference. And you find that there's about a mean of 1 packet in the queue, and the 99th percentile is about 2 packets as the link rate goes up. And the important point here is this is 1 Prague flow and 1 cubic flow competing with each other in a dual queue. And the reason that delay continues to go down, you'll see on the next slide in the dual queue case. It's due to both the coupling and pacing. Now let me explain. So this time series shows you the number of packets in the queue over a time series, but just in the L queue. But bear in mind there is also a C queue here that isn't shown. There's a second queue that is serving the classic flow because it's 1 and 1, remember. So what's happening is when this queue is 0, it allows the C queue to drain its packets. And so you can see it's about half of the time the queue is 0, and that what happens is the coupling from the C queue causes the marking in this L queue to push back the Prague flow until it leaves enough gaps to be about 1-to-1 rate between the 2 flows. And that's why, as the rate goes up, the Q delay gets lower and lower, because we're just, the size of the queue is essentially just the size of the bursts from pacing, which in this case are 2 packets. So you don't have a standing queue at all, and it's not touching that 1 millisecond threshold. It's just being affected by the marking from the C queue coupled across, not by its own AQM. So it's not causing a standing queue up to the 1 millisecond threshold. And so the size of this queue is purely the size of the bursts that come from pacing. So in this case, because the pacing is about 2 packets, you get small bumps with lots of small gaps. But if the pacing was larger, or if the bursts were larger, you'd get larger and fewer gaps. But the next slide, you'll see that if we, this is a zoom in back on the very first plot I showed of the delay versus utilization, but just zooming in on the delay, the one I said didn't stayed flat and the utilization stayed good. But here you notice the delay is not reducing, Even though this isn't a log plot, you can see that. And that's because this is a single flow in the LQ without a flow in the CQ. And so then it is butting up against the threshold of 1 millisecond in the LQ, and that 1 millisecond is configured. So again, the same link rates and round trip times, and the mean and P99 shown there. The red doesn't exist because this is just pulled out, zoomed out of the other plot. It's an inset from the other plot. So it's not a problem that there's a standing queue up to 1 millisecond, because 1 millisecond is small enough. It's just interesting that when you have the traffic in the other queue, the LQ is actually just causing 1 or 2 packets of queuing, not a standing queue up to the threshold. And that insight shows you that if you mark a queue from any other queue that's related to it, you can get rid of a standing queue, which could be useful. For instance, if you had a virtual queue, which some of you may know what a virtual queue is. I haven't got time to explain it now, but it will, it's a queue, it's what the queue would be if your link rate was slightly slower than the real queue. And if you mark with that, you will lose the standing queue, and so you just get the bursts, not the standing queue. So that can be useful. Okay, next slide, please, Jana. Right, jumping to a completely different point, we've still got one flow for each, one steady state flow for each congestion control here. And this is just showing what happens when you have more and more or different numbers of flows of different types. So now along the bottom, instead of link rate and round trip time, we're at one link rate, which is shown bottom left, 40 megabits per second, and one round trip time, 10 milliseconds. But we've got different numbers of flows, A and B. If you look at the little gray box at the bottom, example A2B8 means 2 A-type flows and 8 B-type flows. A depends on the column. On the left column, A is ECN cubic and B is cubic without ECN. On the middle column, no, sorry, am I right? Oh, sorry. I completely forgot. Vidya was meant to be jumping in here because she's got to get a flight. Yes. Janet, can you jump to Vidya's slide? Sorry, I'll come back to that.
Sorry for this interruption. Sorry, it's just I have to take a flight. So we're going to sandwich my results on Apple quick in between Bob's slides. So we have started working on Prague congestion control, as some of you know from the WWDC developer session that we had a few months ago. And these are some early results from our lab testing. And next slide, please. These results are over Ethernet and for upstream traffic. Next slide. As you can see, we tried to do the testing on similar bandwidths and different RTT combinations as they have been done for TCP Prague, just to compare the two implementations. And we see sort of similar results. And in general, if you look at the different results, Prague has almost 90% reduction in queuing delay as compared to cubic. For the low bandwidth case, the 4 megabits per second, I think you see these results because the queuing delay is a little higher because, for 4 megabits per second, to have a 1 millisecond queuing threshold, you need to send less than 1 packet. It's just 0.33 amount of the packet. So that's something we don't do. We don't do fractional congestion window. So that's something to look at for low bandwidths. Next slide, please. This is the application Goodput plotted as utilization. So there's a little bit difference as compared to TCP prog because first of all, we're not plotting the link throughput, but the application goodput, and which includes the link utilization includes header sizes while this one doesn't. And the second difference that we have is we didn't start the measurement at the steady state. So we'll improve this plot to match the TCP prog plot, and this should get to higher link utilizations for both cubic and prog. The important thing to see here is the comparison between the two, and we are able to get similar throughput for both of them. Next slide, please. This is a test done where we have two competing flows. One of them is cubic, the other one is prog. And again, we're measuring the queuing delay for the 25 different combinations. The results are very similar as to what we saw for the single flow as well. And you can take a look at these results on the slides. Next slide, please. This test was done to run 4 prog flows at staggered times with a gap of 10 seconds. And you can see that the first flow start and it has uses the full link, and then the second and the third and the fourth starts, and they start to converge at around between 20 to 40 megabits per second. There is one flow that seems to pop out, and the other 3 flows tend to stay together. And we're investigating the reason for this behavior. Next slide. Comparing prog with cubic, prog is on the left side that I already showed. Cubic is on the right side. And as you can see, cubic is has a lot more variation for throughput for the 4 different flows. Next slide. This is the corresponding smooth RTT plot for the same test, where you can see all these 4 flows, the measured smooth RTT at the quick layer at the end host is staying between 20 and 22, or sometimes 20 and 23. So this is very good result. We have much less deviation from the base RTT. The base RTT here is 20 millisecond, as you can see, and the deviation is very little, and it also reduces the jitter. And next slide, please. And comparing this with cubic, you can see the amount of jitter and deviation from the base RTT for cubic. Next slide, please. So those were the results from Apple Quick. We are continuously working on improving the congestion controller. And now I'll go through a few points that are important while people are getting started on this, and they might have questions on these, so I thought I'll just include that. Next slide, please. Some of the folks asked me whether we need to use Reno for implementing prog requirements, and that's not true. You don't need to use that. You can use your default congestion controller behavior like cubic and use that for reductions and increase during the loss. It's only during the CE you have to change the behavior for prog, and there are other caveats that you should look at the draft for example, RTT independence and pacing. Another thing that's interesting for prog is, when you do a reduction due to when you do a reduction due to CE, and then you see a packet loss right after you did a reduction due to CE within the same RTT, would you want to do another reduction independent of what you reduced due to CE, or would you like to combine the two so that the total reduction is either 30% or for cubic or 50% for Reno. This is something to investigate, and it would be great if folks can try this out and show their results with this approach. Next slide, please. Another important thing for L4S and Prague is pacing is mandatory, because otherwise you will create burstiness and you will see a lot of marks. And for pacing, there are obviously things to consider, like if your congestion control is in user space, for example, Quick protocol has congestion control in user space. What kind of pacing would you want to use? Because you need more fine-grained pacing than what you might have been using right now. So if you use user space pacing, you could have skew in timers that could basically cause some amount of bursting if the pacing is not accurate. On Linux operating system, there are ways to offload this to kernel. There are APIs like socket max pacing rate and SOTX time, and you need to use fair queuing discipline for both of them. And some of the quick implementers have already tried SOTX time, so they have some experience, and you can try either of the approach and decide what works best for your implementation. For the congestion controllers in kernel, some TCP still exists in the kernel stack. So for that, it's pretty simple. On Linux, you can use the SK pacing rate on the SK, and then you have a callback for TSO segments, which allows you to set the burst size. So that is all from me today. As I have to leave now, so if you have any questions, you can ask Bob. And if Bob doesn't have those answers, please feel free to send questions to the mailing list. Thank you.
Thank you. Sorry. Safe journey. Yeah, sorry, Jana, can you, does anyone want to ask Biddy questions? No, she's probably wanting to get off, isn't she? Okay, one back, yep. So here, this is a plot of normalized, this is now going back to TCP Prague. So Biddy was implementing Prague in Quick. This is going back to the Linux implementation of TCP Prague before we had to let Biddy in so she could get her flight. Right, this shows along the bottom different numbers of flows. For instance, A2B8 meaning 2 A flows and 8 B flows. On the left, they're all ECN cubic. On the right, they're all Prague in CODL. And in the middle, they're Prague versus cubic in a dual queue. So the cubic ones go into the classic queue and the Prague ones into the other queue. And the aim is obviously to get roughly hit the ratio of 1, but it's not a ratio, sorry, it's a normalized rate per flow, where 1 means your flow is going at 1/n of the capacity where there are n flows. So along the bottom, you see you've got A1, B1, A2, B2. So for A2, B2, n would be 4, and you're getting, if you're getting a quarter, then the normalized rate would be 1. And you'll see about halfway along, it also starts testing A0, B10, A1, B9, A2, B8. So we have actually tested the full matrix, but this gives you representative results. And you can see that FQ-CODL is pretty spot on 1 all the time, with very little variance, if none, apart from the odd bump and fart, which they are in fact hash collisions, given we did a lot of tests on this. And on the left-hand column, you can see that pi is similarly, the mean is sitting at 1, but the variance is greater. I should add that the top plot is cubic, and the bottom plot is cubic versus Reno as the other flow. So the top is cubic, and the bottom is cubic Reno for the pi and for the pi case, and the middle is pi cubic at the top and pi Reno at the bottom. And you can see in the middle the dual pi squared. It's not quite on 1, but it's not far off. It sort of wanders around a bit, and the blue one is sometimes above 1, sometimes below, but not significantly far off. But the classic flow has a similar variance to the pi one, and the Prague flow has a flows have a similar variance, but well, not quite as good as the FQ Coddle one by any stretch of the imagination, but pretty good. I'm going to jump over the point with the grey call out in the interest of time. So please, you should be able to read about that, or we can talk about it on the list. Next slide, and then I think we're pretty close to done. So this one is now with mixed round trip time flows, which has been a point of contention with the dual Q algorithm. So we solved this using an RTT independence approach within Prague, within TCP Prague. And here, just to explain the plots, again, you've got A number, B number, and that this time the numbers represent, again, if you look at the key at the bottom, they represent different round trip times. So something like A5, B100 means 5 milliseconds versus 100 milliseconds. And it tests, A is always Prague in the middle column, and B is either cubic or Reno, top or bottom. Sorry, not top or bottom. Reno is the red triangle, and the black star is cubic. And the top one is rate ratio, and the bottom one is window ratio. So you'll see FQ Coddle gets the rate ratio pretty much 1-to-1 because it's a FQ scheduler, so you'd expect that. The single Q variance on the left, pi, you'll see the rate varies with round trip time across that sweep of round trip times, but the window stays pretty much close to 1 because they're window fair. Whereas on the right, you can see the window is pushed into being different because the rate is equal. Now, dual pi squared effectively emulates a single QAQM by this RTT reduction algorithm that's in it. It's just slightly worse. So you can see that the worst case is 6.3 a ratio rather than 5.5, so that's 1.14 harm metric, if you like, worse. I won't go through all the writing which I've put on there for anyone who wants to study this in their own time. Okay, next. Thanks, Jana. Oh yes, this is the last set of plots. This is now the first one that isn't steady state stuff. We to give a feel for what happens when you've got web-like load. This is heavy web-like load plus a long-running flow from both flows. We've got cubic ECN versus cubic non-ECN on the left-hand column, and the right-hand column, left-hand being pi, right being FQ Coddle again. Middle is Prague versus cubic. So all the time we're trying to compare ECN versus non-ECN, so we cut out any effect of ECN itself. The plots along the bottom two plots are Q delay and utilization again, as at the start, but this time remember with a lot of short flows as well. And there's a very heavy load of short flows here. And you can see the Q delay is pretty much like it was before in the dual pi squared case. In the FQ Coddle case, it's quite a lot worse, particularly at the low round trip times, because if you look at the scale there, it's auto-scaled up to nearly 250 milliseconds at the 99th percentile on FQ-CODL. And utilization is probably best on the Pi one, but the profile of the utilization is pretty much the same for the dual Pi squared and FQ-CODL cases. And really the point here is that the way Prague works, the long-running flow has an EWMA in it, which recognizes there's a load here of unresponsive short flows, and it makes some headroom for them to keep the delay down. And that was all part of the design of DC TCP, and that's what we wanted for the internet. The top plots are cumulative distribution functions, and they're complementary, and they're also log scale. I have shown one of these before. So along the bottom scale is the Q delay, and the vertical is percentiles on a log scale. And each one of those is just one case of the other. You know, as I mentioned before, there are 25 cases, and it's just picking one of them, 120 meg, 10 millisecond case in each case. And the gray background plots are the ones off the other plots. So it's picking out the two that are in that, either experiment 1, experiment 2, or experiment 3, but you can still compare it with the others. And as you can see, the blue Prague one there is right down, much lower. Even at the 5/9 percentile, it's about 6 milliseconds. At 99th percentile, it's about 2 milliseconds. So that I've shown you that plot top middle if you've been in any presentations about L4S before, and it also shows where FQ-CODL is and Pi on the same thing. But just to point out that that is sort of seeing FQ-CODL in a good light, because it's picking one of the better ones for FQ-CODL. Okay, thank you, Jana. I think there's one more slide plus a sort of final, yeah, just a summing up slide, I think. Yeah, so the messages are, if you don't want a standing queue in your buffer, control marking from another queue, possibly a coupled queue or a virtual queue. Secondly, the proper place to address round-trip time dependence is in a congestion control like Prague, which is being newly deployed for low latency, which is where the problem is. And third, long Prague flows leave headroom for the short ones. And that's a feature that's intended for the utilization to be reduced when you've got a lot of short flows that are unresponsive effectively. And just finally to say, these results, we use these sort of plots to check for regressions, and these have been stable since about, that says July 19. I think this is probably, Jana, the first version of the plots I sent you. I think a new one says we can go back to 2016 and they're stable like this. Okay, any questions for either me or Biddy? And I'll try and channel it to Biddy. I can't see you, by the way, because the projector's...
I'm gonna step in here very quickly. We don't have a lot of time, so let's take one or two quick questions. I need to switch. Do we have people there at the mic? I don't see anybody at the mic, but there are a couple of discussion questions on the chat there, Bob. That might be something that if you can get back to your laptop, you can respond there.
Jenna, I'm having trouble understanding you. Can you just speak?
That is a problem in my life in general. I said we'll take a quick question.
Right. Yep.
John, you're on the thing. Go for it, Jonathan.
Okay, now as you probably know by now, I'm going to be quite critical, but I'll try to keep it sensible for this particular group. So, first question is, you mentioned that it would need a very smooth pacing in order to reduce burstiness. What happens if burstiness is introduced by the link?
Right. Yes. So that's actually semi-answered by the point about marking with another queue. And I mentioned if you mark with a virtual queue, you can ensure that any bursts coming into your L4S link, whether if caused by, like you say, another link like a Wi-Fi upstream or something, they will still come into the L4S AQM, and the flow will still hit the threshold. But if you put that threshold in the virtual queue, it at least will ensure that the bursts don't get into the real queue, even though so effectively it will reduce the utilization of the bursty flow up to the, well, it depends where you put the threshold in the virtual queue. You can absorb some of the burst in the virtual queue, and then above that the burst will go into the real queue. But the reason for doing that is that what you don't want to do is to set the threshold in the real queue. I mean, say for instance you're getting 10 millisecond bursts. You don't want to set the threshold at 10 milliseconds just in case you get bursts. And then when you don't get bursts, you get a standing queue up to 10 milliseconds. Whereas if you put it in the virtual queue, you will get, when you have bursts, you will still get bursts in the real queue, or at least the top of them. But when you haven't got bursts, say you've got an Ethernet link coming in as well, and you've got traffic coming over that, then at least you will have the smoothness of that link. So the aim here is not necessarily to get rid of the bursts from the Wi-Fi, although that would be another possible approach where you put a shaper in or something, but only if you really knew that you had the burst in the first place. But it's more to make sure that you don't configure your thresholds just in case you've got burstiness if you haven't always got it. So you get the benefit of smooth links when you're using them, and you can still absorb the bursts from the bursty ones. Is that a oh, and I should add that virtual queue is in the design of DOCSIS from the start. We would have to add it to the Linux implementation to test it, and we haven't tested anything I've just said. That's just how I believe we'll be able to do it. But I have started doing this with my colleague Joachim Missun.
Right.
I'm going to say here, hang on. We need to move on to the next one, and I encourage you to continue this conversation on either the chat channel or on email. Bob, we have 15 minutes left, and I've got 2 more things to do. So, thank you, Bob, Vidhi, for the presentation. I do appreciate it. There's some, like I said, there's some feedback on the chat. Please go take a look. I'm going to switch over to Natali. I'm also going to try to come here and eat your head from here as you leave. Let's see if I can do that. I can't do that. I was going to eat you up, Bob.
So, hello, can you hear me?
Yep.
So, hello everybody, my name is Natalie Romo Moreno from Deutsche Telekom, and welcome to this presentation about packet reordering in multipath transport scenarios. Next slide, please. Should I control it, or do you have the control? Okay, perfect. So I'm going to start with a brief introduction explaining the problem that we try to address here, and then I will show some experimental results and conclusions. So first of all, when we compare multipath transport with single path transport characteristics, we know that in the case of the multipath scenario, we experience an extraordinary higher jitter and also a significantly higher out-of-order delivery. This comes precisely from the heterogeneous nature of the different paths which are bundled within the multipath connection. Now, these characteristics, this high jitter and high out of order, are exposed by the multipath protocols either to the higher layer application that makes use of them or to the end-to-end traffic that is carried by them in the case an intermediary multipath transport is used, as it is the case of the ATSS framework specified in 3GPP, which defines a 5G and Wi-Fi MNO bundling. So from the MP protocols, those who have a strict reliability and strict in-order delivery like MPTCP and MPQuick in stream mode, they only experience a high jitter dominated by the path latency difference. But for those protocols which do not have this strict in-order delivery like MPTCP, MPQuick with the datagram extension, and SCTP with the CMT extension, we experience jitter as well, but we also experience a high out-of-order delivery, also dominated by the path latency difference. Now, the problem is that the services running over the internet are designed to cope with the characteristics of the single path transport. So if we add this high jitter and this high out-of-order delivery introduced, for example, by an ATSS splitting use case, this might result in quality of experience and quality of service degradation. So coming from this statement, what we did was to conduct some work to investigate the demand of multipath reordering and latency difference compensation, precisely in the scenario where an intermediary multipath transport is used, as it is the case of the ATSS splitting scenario. In a first stage, we demonstrate the impact of no reordering with different traffic types carried over a multipath transport. And afterwards, we evaluate different solutions to correct this out-of-order delivery and this jitter. The explanation of these algorithms that are going to be shown here is also in this draft that I linked in the presentation. So the tests that we executed were executed using the MPDCCP framework, but the results are also applicable to other multipath solutions like MPQuick. We generated traffic TCP UDP using Iccrg, and we also generated quick traffic using the Quick Go implementation. Next slide, please. So, as I said, in an initial stage, we demonstrate what happens when there is no reordering at all. So for this test, we used plain UDP traffic and quick traffic over a multipath DCCP connection. The MPDCCP connection has two subflows or two paths, each one of them with a 10 megabit per second capacity, and the latency difference between them is of 15 milliseconds. We use a priority-based steering mode. That means there is a primary link that is going to be used by default. Once the primary link is congested, the secondary link will start being used. And the congestion control used in the quick traffic is Neurin. So in the left, we see the results for the UDP traffic. We see that both links are fully utilized and that we achieve full aggregated bandwidth. Okay. And to the right, we have the quick results. And then we can see that only one path is fully utilized, even if the secondary path is attempted to be used sometimes. So what happened in the quick case is that as soon as the secondary path starts being utilized, the path latency difference causes a lot of scrambling. This scrambling causes duplicate acknowledgements, which are an indication for the quick protocol of packet loss. So the reliability mechanisms and the congestion control react immediately. There is a packet retransmission and the congestion window is cut, and therefore the throughput is also reduced. So at the end, we end up utilizing only one path. In conclusion, for a protocol like UDP, where there is no any congestion control or any reliability, there is also no need of any no demand of any reorders. So the scrambling introduced by the multipath transport doesn't have any effect on the overall performance. But unlike UDP, which has a congestion control, and therefore there is a demand for in-order delivery, and therefore it fails to use the aggregated bandwidth due to the impact of the packet scrambling. Next slide, please. So now that we demonstrate that there is an impact when no reordering is in place, and that this impact is also correlated with the characteristics of the carrier traffic, we proceed to evaluate some solutions to correct this out of order delivery. The first one is a reordering algorithm based on connection sequence number with an static timer. So what we do here is basically read sequence number to verify the in-order arrival. If a gap is detected, there is a buffer which stores the received packet until the missing one arrives or until our fixed timer expires. In this case, we use the same setup as we had before. We use quick traffic because we know there is an impact over this type of traffic, but with the only difference that we introduce a reordering algorithm with an static timer of 50 milliseconds, which is higher than the path latency difference and therefore enough to correct all the scrambling. The results are shown in the figure. In this scenario, we managed to fully utilize both paths and to have the full aggregated bandwidth close to the 20 megabit per second. So basically, the reordering algorithm in this case corrects the scrambling, eliminates the duplicate acknowledgements, and therefore prevents the congestion control in the quick stream to react. And as a result, the application manages to fully utilize both paths bandwidth. Next slide, please. So this reordering with the static timer works well as long as we know what the path latency difference is and if this latency difference doesn't change. But there might be the case where this latency difference goes either above or below the timer that we configure. So this is what we try to test here. We have the same setup as before, but we have a path latency difference of 20 milliseconds and a timer of only 15 milliseconds. The results are in the graph in the left side. So we see that the secondary path is not fully utilized and there is an impact on the overall aggregated bandwidth. To correct this problem, the solution that we test is the same reordering based on sequence numbers, but with a dynamic timer. This dynamic timer is going to be updated to be equal to the latency difference of the paths. And this latency difference is going to be estimated using the RTT measurements provided by the congestion control in place. So we see the result to the right, and we see that it works. We have, again, both paths fully utilized and a full aggregated bandwidth because the timer manages to adapt to the network conditions and the scrambling is fully correct. Now, at this point, we prove that this sequence-based reordering solves the problem of the scrambling. So there is no more scrambling and a congestion control like new Reno doesn't react anymore. But this sequence-based reordering doesn't do anything with the latency difference of the paths. So we still have the problem of the high jitter, even though the new Reno doesn't react to that. Next slide, please. No, there's one before. There's got to be one before. Yeah, that one. So now the question is what happens when the congestion control is not a loss-based congestion control, but a latency-sensitive congestion control like BBR. So to test that, we use TCP BBR carried over our multipath TCP framework. We have the same setup of the static reordering with a timer higher than the path latency difference. So we know that the scrambling is corrected, but we still see that only one path is utilized. And this happens because for a congestion control like BBR, which is latency sensitive, the jumps in the latency generated by the scheduling through both paths generate a throttling of the throughput under the assumption that these peaks in the latency come from buffer bloat. So to correct this problem, we test a solution which is the delay equalization or the path latency difference compensation. What we do with this solution is that at the receiving side, we delay the incoming packets in the fastest path to equal the latency of the slowest path. Again, this delay has to be equal to the path latency difference that is estimated from the RTT measurements. The results are in the right, so the correction of the latency difference or the equalization of the latency in both paths solves the problem of the reaction of the BBR congestion control, and we have, again, full utilization of both paths and full bandwidth aggregation. And next slide, please. So to summarize all these things, we demonstrate that there is an impact when no reordering is used, and we also demonstrate that this impact on the performance varies depending on the characteristics of the carried traffic or service in the multipath transport, and therefore different solutions are suitable for different traffic types. Now, within the ATSS splitting scenario, the characteristics of the traffic carried over the multipath network might be unknown. So in this case, we need certain in-network reordering mechanisms to guarantee an optimal performance. Additionally, all the results that I presented here and additional one with more analysis were presented in the 3GPP SA2 working group. And there it was also concluded that in-network reordering support is required. In this document that is linked in the presentation, it is also recommended that to achieve an optimal performance, it is better to use a combination of all these solutions together. So a sequence number based reordering with a dynamic expiration timer, a delay equalization, and also some algorithms to detect fast packet loss detection. Next slide, please. Now, the question here is how this fits into IETF scopes. So far, reordering and latency difference compensations for multipath protocols is not standardized at all, similar to what happens to schedule it within the multipath context. Both are so far out of the scope of serious standardizations. There are some individual informational drafts about it, but therefore are implementation specific. Without a specification, a consistent behavior between client and server in down and uplink direction is not ensured. And also these scheduling and reordering algorithms are mainly agnostic to IETF protocols. So they will not be part of the standard of MPTCP, MPDCCP, or MPQuick. So our question here is, what is the right place or where is the behavior in IETF to address these multipath overarching topics like reordering and scheduling? That's it. Thank you very much. If you have any questions.
Thank you, Natalie. I
comments.
think this is Magnus is in the queue. Magnus, if you want to respond to this quickly, that'd be great. I want to switch to giving Colin a couple of minutes before we leave the room. Go ahead, Magnus.
Magnus Westlund. Your new Reno, did it include rack?
Sorry,
Did
I couldn't.
Did it include any rack functionality?
No, I just tested with the default configuration of the Quick Go, so that was basic new Reno.
Okay. So I guess it would more likelihood behave slightly better, but anyway. And when it comes to this, I think what you're actually asking around the IETF scope here, it's a question of when you're tunneling over an MP. If you have an application protocol on top directly on MP, this is not the question. It's only when you're doing tunneling and have another flow. So it's a question of tunneling over MP protocol when this arises.
I'll say, Natalie, that there's a conversation in terms of where does it fit in the IETF. I encourage you to reach out over email, and I can pull the right people in. But please reach out over email, and I'm happy to take it from there.
Sure.
Thank you for your presentation again. Before we leave the room, I know we are past time, but I just want to give Colin a couple of minutes to talk about. Colin, are you there? To talk about congestion control work in the IETF. Go for it, Colin.
All right, thanks, Joanna. So I just wanted to give people a little bit of a heads up for some work which is potentially happening in the IETF side of things. So those of you who were in the transport area working group earlier in the week or on the transport area list will have seen that the transport ADs are considering chartering a new congestion control working group in the IETF. A lot of the goal of that looks to be to update RFC 5033, which is the guidelines for how the IETF standardizes congestion control algorithms. But there's also suggestions that the group will consider developing standards track congestion control algorithms after that. This obviously raises a number of questions about the relation of this group and what's happening in ICCRG. The expectation I have is certainly that ICCRG is going to continue in the IRTF as a home for research and experimentation on congestion control, and it will continue to be separate to standards track work in IETF. The expectation, I think, from the IETF side is that proposals for standards track congestion control algorithms will have been pretty thoroughly vetted by the research community before they get to the IETF, and I expect ICCRG will certainly play a role in doing that. And in facilitating discussion, providing review of the documents. And I think ICCRG is a really good venue for people to talk about this sort of work. It's got really strong links to the research community, and I think it really sort of helps to add value when just by allowing the researchers, the industry, the standards community to exchange ideas. And the work in ICCRG has been really good at getting practical experience, getting researchers, implementers talking to each other. And I think that's really important, and I hope it continues. ICCRG is also going to continue to be able to publish our experimental RFCs. They're a really great way to document congestion control algorithms, and I think that they're especially important perhaps as a way of documenting things that are perhaps hoping to move into the IETF standards track, just as a way of clearly describing the baseline. That said, I don't expect ICCRG to turn into an experimental RFC factory. It's a venue for your research, experimentation, and discussion, first of all. So, yeah. I think Jan has been doing a great job as chair. I'm expecting and hoping that he will continue as chair of the group, but we are certainly looking to appoint new co-chair candidates to help move things along in ICCRG, and Jana and I are talking to some potential people in that space. So that's what I think is happening. If there are any questions about it, I'm happy to try and answer them from the IRTF side, and I guess talk to Martin Duke in the IETF side if there are questions about that. I don't know if any of the transport ADs are in this meeting. Thanks.
Yeah, I seem to have walked in at exactly the right moment. Martin Duke from Google and Transport AD. Yeah, so I just to be clear, I completely endorse everything Colin has said. I think he and I are in complete alignment about the vision here, and I in fact insist that ICCRG continue to exist and do what it has been doing, if not more. A very possible outcome is that we do this congestion control working group, and it completes its assigned tasks, and there's little, if any, standardization effort, and the group closes, and like ICCRG will still be there as a congestion control forum as it has been for years. So yeah, I just wanted to just be absolutely clear about our complete alignment on this. Thanks.
Thank you both, Colin and Martin. I think by the next meeting, we should have a lot more clarity on what's going on. So I would encourage people to stay tuned and definitely show up to the next ICCRG meeting and the next IETF. Of course, both of those will have some interesting bits for those interested in congestion control and how that work is done in the iStar space. So with that, thank you, everybody. Please enjoy the amazing heat in Philadelphia. I, for one, will not have to deal with that, but hope you have a wonderful rest of your week in IETF. Thank you.